Hello, this is my second video in a playlist that I have titled Generalized Linear Models. And this specific video deals with the canonical link function. And I have two background videos, GLM background, and really it's more than just a video. It's a playlist of videos which I call the Exponential family. And there we go in and we calculate the mean and the variance of the general exponential distribution and then show that lots of different distributions fit into this exponential family of distributions. Okay. So for this video here, well, for generalized linear models, it's what's called a dispersion exponential family or over dispersed exponential family of distributions. And so this is the density that we assume when we do multiple or generalized linear models. This right here is called the canonical parameter, theta. And so we try to fit the distribution into canonical form of the exponential family. And a couple important notes here is that this right here we assume it's y, and that's our sufficient statistic. And so in several distributions, when you put it in the canonical form, you don't get this. And for an example, if the chi-square distribution fits into the exponential family distributions, but when you put it in the canonical form, this right here is the log of y. Okay, it's not y. And one reason we need y is it can be shown that the mean of this sufficient statistic is actually the first derivative of this log partition, or b of theta. And we model the mean of y. So it comes in very handy that the mean of y is just the derivative of this log partition. And so we don't want to deal with distributions that don't just have y or the data as the sufficient statistic. And so you might be wondering, I was like, the canonical link function, but can't we use just general link functions when we do generalized linear models? And the answer is yes. And we'll do that in later videos, but these first few videos following this one is going to be dealing specifically when we're using the canonical link function. And there's lots of different cases where this applies. So normal distribution, of course we have to assume we know the variance. Poisson regression, binomial regression, or logistic regression with the logit link function, that's the canonical link function. Exponential distribution, negative binomial regression, gamma regression, multinomial regression. So this applies to a lot of different situations, but I think, or at least in my opinion, it's kind of easier to start with this and then expand to the general case. Okay, so here what we do is the canonical link function, and this is called the canonical parameter. And so in this setting, we assume this canonical parameter can be represented by a linear combination. So the x's and the betas, and that's what we assume here. And so this can really be replaced by x's and betas, and we'll get to that. Okay, so the link function is this. So the link function, so we know from BV2 and BV1 that the expected value of y is actually the derivative of our log partition. Okay, so B prime is a function of our canonical parameter. Okay, so really we could call this anything, h of theta, m of theta, but let's call it g inverse of theta. And so this is just the way to give it a name. Instead of calling it, the first derivative of b of theta or the b prime of theta, we'll call it g of theta. Then how do we solve for theta right here? Well, if we take g, apply g to both sides, then we get this. So G of mu and G of, of G negative, we get the theta back, okay? This is our canonical parameter, and we're assuming that that canonical parameter is a linear combination of betas, x's and betas, okay? Now, G is called the link function, or in this case, it's the canonical link function, and really, when we apply a function to our mean, and we get the canonical parameter back, it's a canonical link function. And then we're going to let this canonical parameter be represented by a linear combination of the x's, okay? So here we assume that theta is, the canonical parameter can be represented by this linear combinations. In later videos, we'll assume a more general approach. So we're going for the canonical link functions in this video. Now, and that's it. So, and that's a canonical link function. But one question is, how do we know that B prime has an inverse? We don't know that, at least yet. We called it G inverse, which sort of implies that we can take the inverse of it and solve for theta. So the next theorem deals with showing that B prime is strictly increasing. It's a strictly increasing function, which means we can take an inverse of it. So theorem 1, B prime is strictly increasing, which implies that it has an inverse function, which means that we can do this. The canonical link is the inverse of B prime. So the proof goes like this. Oh, and one note is that we're not going to consider thetas, or the canonical parameters that have a distribution centered at one point. So meaning the variance is 0 if theta equals a certain value. Let's not consider those, because in practice we never consider those. So, but theoretically you should, for this video, that's a possibility. But if we say that we're not in that setting, then it's not a possibility. And so by BV1, we know the variance is this. So it's the second derivative of the log partition times phi divided by W, okay? And since it's the variance, we know it is greater than or equal to 0. But the equal part is what we're going to ignore, because when the variance of y equals 0, that means all our mass is condensed on one point, and realistically we never model anything like that. It's always a range of values. So we're going to assume it's strictly greater than 0. Now, we also know phi is positive, and W, the weight, is positive. So if we multiply those to the other side, we get that the second derivative of theta is positive. So now let's let theta 1 and theta 2 be arbitrary parameters, and theta 2 is greater than theta 1, strictly greater than 1. And so by the mean value theorem, there exists a C in this interval such that beta double prime of C is equal to this, okay? So beta prime of theta 2 minus beta prime of theta divided by theta 2 minus theta 1. And then that's equal to, the derivative of one of these functions, which is this. But since we know that beta double prime of theta is always positive, we know this is always positive. And then so if we multiply this to the other side and then subtract that over, that implies that beta prime of theta 2 is strictly greater than beta prime of theta 1. So therefore, beta prime is strictly increasing, which means it has an inverse function. Okay, so last page. So a quick definition, a convex function. So if it's a differentiable function of one variable, say call it f, is convex if and only if the graph lies above all of its tangent lines. So f of x, which is this, lies above all the tangent lines. So pick a point, find a tangent line, and the graph, entire graph, is above it. So this is one way to define convex functions. So theorem 2, B is strictly convex. That's a theorem. So in the previous theorem, we talked about B prime, or the derivative of B is strictly increasing, which then it showed it had a derivative. So the proof, by theorem 1, we know B prime is strictly increasing. So let's let theta 1 and theta 2 be parameters such that theta 2 is strictly greater than theta 1. Then by the mean value theorem, there exists a C such that C is in this interval, well, C is contained in this interval, such that beta prime of C is equal to this. So B of theta 2 minus B of theta 1 divided by theta 2 minus theta 1. This is, by the mean value theorem, this relationship holds. Now, if we kind of solve for and isolate B of theta 2, that we get to this situation. So we multiply up and then add over the B of theta 1. We get to this situation. But we know that B prime is strictly increasing. So if we put a smaller number in here, remember this is a number because we're evaluating it at C, so it's a slope. So if we put, say, B prime of theta 1, and since C is in the interval here, we'll put the smaller value in here, and then it goes down. So this is smaller than this. But this right here is a line tangent at theta 1, right? That's a slope at theta 1, at theta 1, B of theta 1. And so that's this setting. And we know that B of theta 2 is strictly greater than that. So if we draw a picture of what just happened, so we have our function and we create a tangent line, we just showed that the function value at theta 2 is always strictly greater than the value of the tangent line, okay? But since theta 1 and theta 2 are arbitrary, this works for any 2 points in the tangent lines that we create. So since they're arbitrary, the theorem follows. And so what we just proved here is that the properties of the function B, the log partition, B is strictly convex. The first derivative is strictly increasing, which of course allowed us to have an inverse function. And we know the second derivative of the log partition is strictly positive for all parameters, or all theta. Well, that's all I have for today. Hopefully you enjoyed that. I sure did. There's more to come. And if you like it, please like the video and subscribe so you don't miss the next one. Thanks. Bye.